Physics Penguin.
Welcome to Physics Penguin's Guide to the National Grid. Today we will be looking at how electricity gets sent all over the country. The types of power station get explained in the energy topic, and how they work is covered in the magnetism topic, so there are a lot of links to other work here. Let's have a look at this diagram. It shows a small section of the national grid, and it starts with the power stations. We have small electric power producers like wind turbines or solar panels, or something huge and powerful like a hydroelectric dam or a nuclear power plant, but they all connect to the national grid. In recent years, many people have made their own electricity and sold it to the national grid. Their houses would be taking the place of the power station in our picture. Most generators produce quite a high voltage or PD, but for reasons we'll see in a minute, we need a very, very high voltage to send it a long way. 400 or 500 kV is normal. 1 kV is 1000 volts. We're talking about around about 500,000 volts here. To change the voltage, we use a magnetic device called a transformer. We'll look at them in detail when we do magnetism, but for now they just change voltages. A step-up transformer increases voltages, and a step-down transformer makes iced lattes. No, it doesn't. It reduces voltage. Just testing. After the voltage is boosted at the power station, the power is sent into the network of power lines held up by pylons. The network of cables goes just about everywhere in the country. Sometimes we hide them by burying them, but that is expensive, so mostly they just hang on their pylons. By the way, in winter, when it's cold, the wires shrink and the lines are quite tight, but in summer they heat up and sag a little between the pylons. Eventually, these lines will get to their destination. The voltage or PD is way too high to safely use for most things, so we need to step down transformers to change voltage into something better. On the diagram, you could see that sometimes the PD is lowered and then lowered even lower again to be used by houses and shops. Some users need quite high voltages though, because they need a lot of power, like the railways and factories. The people who work with electricity supply for these users need careful training. Watch out for the warning signs near railways and factories, they aren't kidding. Sadly, many young people get badly hurt or killed by high voltage electricity. Now the key bit. Why use high voltages at all? Well, it comes down to power. P equals IV. If you had a power plant and made a lot of electric power, you could give people a high I, a current, and a normal voltage, or a normal current and a high voltage, V. The problem is that high currents get wires hot, and hot wires mean that heat energy is escaping. The more energy that escapes the wires, the less gets through to the users. High voltages can keep current low, which means much less energy loss. The downside is the increased chance of sparks. Electricity can jump about 1 centimetre for each 30,000 volts in dry air, but much further in wet or humid conditions. Our 500,000 volt power lines can make a spark that is at least 17 centimetres long and possibly much longer. If you walk under a pylon, you can hear the crackling of tiny sparks jumping to the pylon itself. Never mess with power pylons, they are death traps. Well, that is about it for the main part of this week's work. Now it's time to download the worksheet from the description and complete the nice diagram. Pause the video and I'll go over it later. Okay, welcome back. Let's have a look at that diagram again. Let's do the labels first. The first box is the power station, obviously. The voltage should be 25 kilovolts kV. This next thing is a step-up transformer. It connects to power lines at 400 kV, then into step-down transformers for factories and homes. The home voltage is 230 volts. Now let's fill in the gaps of question 2. Power stations generate electricity. This is transferred to our homes through a series of pylons and cables called the national grid. To reduce energy losses, it is transported along power lines. A step-up transformer is used to change the voltage. If the voltage increases, the current decreases. Remember, power is current times voltage. This reduces the loss of energy in the form of heat. Before the electricity reaches our homes, the voltage must be decreased using a step-down transformer. Finally, let's try question 3. Why decrease the voltage to homes? Well, the simple answer is that we can't have sparks in our house, so we reduce the voltage to keep the sparks tiny. The more complex answer involves power. If I am grilling bread in a toaster, I need the wires to be hot. If I used a 400,000 volt supply, not only would massive sparks leak between the wires, but the current in the wires would be low, so the wires don't get hot. Double whammy. Well, that's it for this week. Go back and check anything that you're not sure about. Don't forget to subscribe to get informed when new videos are available. Take care. This is Physics Penguin saying ta-ta.
Physics Penguin.